Hi, I'm Vikram. I will be presenting one FRB, and so this talk will be about 9 times slower than Ryan's, uh, which hopefully will be nice, but it'll also give you a little update on the kinds of work we're doing at Caltech to build a dedicated FRB localization array. Um, these are just two of the first 10 dishes that were used in our prototype. So this whole story started off with these debates, rather acrimonious debates that we used to have some years ago about the FRB log n log s or log n log f for fluence, and I really look forward to not thinking about this again. And I certainly don't think about it at the moment, which is kind of nice because we have FRBs, we don't need to really think too hard about this in designing telescopes. But the idea back in 2016, and I blame this entirely on Harish Vedantam sitting in the back there, was that the Parkes detections in multiple beams of the 13-beam multi-beam receiver indicated a preponderance of bright FRBs. There were probably a few more bright FRBs than we expected at the time. I show here sort of a evolution in the slope of the source counts, alpha, with time, where Shri Kulkarni very publicly communicated to us that it should be 1.5. We had J.P. McHart and Simon Johnston claiming a slightly steeper source count, which has persisted, I think, among the ASCAP group with time. However, on the other hand, we were brave enough to claim a slightly shallower set of source counts at Caltech, which motivated us to build a telescope that was not very sensitive, but could see a wide field of view. And because, of course, the slope for source counts is shallower than 1, the wider your field of view, more FRBs you see, regardless, for a fixed sensitivity of your telescope. I'd also like to point out that source counts are very hard to interpret. I show here a plot from a recent paper where we basically made different kinds of source count distributions for different FRB spectra, as well as simply observing at different frequencies. In both cases, you can make different kinds of source counts, which really don't tell you all that much if you don't know either the intrinsic spectrum or and how your observing frequency relates to that. So what we did is we tried to optimize the dish diameter given the range of source count slopes that we thought were real. We picked a diameter of 4.5 meters. What we found that we could design was something with a sensitivity, search sensitivity of about 6200 Jansky, which is a little worse than 3 times as bad as a single ASCAP dish. We're very brave. Our frequency range was about 250 megahertz at L-band. We had plenty of channels, and digital stuff was not our problem. We had plenty of channels, plenty of time resolution, so on and so forth. The key thing being that with a maximum baseline of about 1,300 meters, we could localize to 5 arc seconds, assuming a boost in signal to noise when we coherently added all dishes. And so we bought the dishes from Alibaba.com. Here's one in a proposed assembly, $1,700 including shipping. They came in one container. Dr. Sandy Weinreb put a huge amount of effort into designing various aspects of the analog receivers, including custom feeds. Those are real cake pans from a company called Fat Daddy-O's. I forget exactly where it is, but they're actually cake pans that were found to be the right size to act as a choke. Our feed range was very sophisticated. We came up with a configuration based on existing infrastructure at the Owens Valley Radio Observatory, with 9 dishes on this T over here, and 1 sitting way down there to give a long baseline. Our PSF had maximum side lobes of about 50% of the peak, which is fine. There are 4 dishes. They don't move. They just point at the meridian and can be manually steered along the meridian. And so we saw an FRB in the middle of 2019. You can see on loop the pulse appearing in this image. The image is rather large with 5 arc second pixels, and it's at 131 microsecond time resolution per frame. So there are about 4 frames where the pulse is evident. the system works. That was sort of the main message there. And the pulse, of course, was rather bright, somewhat over 280 Jansky milliseconds. The spectrum shows a rather characteristic patchy nature with perhaps a bit of emission up there and some patches down here too. And we saw a bit of scattering, about 1.4 milliseconds worth at a gigahertz. And within, I think the sequence of events was the FRB occurred towards the start of an observation. 6 days later, I stopped it and realized we had an FRB. 2 nights after that, we had a spectrum from Keck. And then within a week, the paper was submitted and published, I think, a couple of weeks after that. And so here's some images from Keck. I'm not showing the spectrum here, but as you can see, our localization region is not excellent, especially compared to the ASCAP results. We were pointing rather far north at a chime repeater at the time, but of course we didn't see the chime, the repeater. We saw this, and I just want to emphasize that the inner region is 1 sigma, 2 sigma, and 3 sigma as well. And so with at least 90% confidence based on Taranay's statistics paper, we associate this source S1 with the FRB. I'd like to note that part of the significance of that association is due to a good agreement between the DM, which is about 760, and the redshift of the galaxy, which is about 0.66. I'll also point out that this S2, also as pointed out by X. Prochaska, is rather closer at a redshift of 0.36, which is also the redshift of this little thing over there, which is kind of nice. And what we also found, which was rather exciting to us and also nicely consistent with some of the early ASCAP results, was that the galaxy was relatively massive based on spectrophotometric modeling of the SED. And also, we were able to set an upper limit on the star formation rate of about 1.3 solar masses per year. This upper limit was inflated, I would say, by the detection of an O2 line, which is almost certainly an AGN line, but we haven't quite gotten around to getting a near-IR spectrum to look at the H-alpha, for example. And so we have this teeny little line, which is probably an AGN line, but we have to interpret that as star formation and thus set the upper limit on the star formation rate. Just from the SED, the upper limit is somewhat under a solar mass per year. And so that's the FRB. And it's great because I've got about 6 minutes to tell you about what we're doing now. At the moment, we are beginning construction on the DSA 110, a 110-dish array on the same site, on the same T-shaped infrastructure, but now with a 95-dish core sitting over here, and extended baselines all the way out to 2.5 kilometers around the boundary of the site. This array is fully funded, and we've passed our final design review in, I think it was in November last year. And we initially spec'd the thing to be sensitive to a 1.1 Jansky millisecond FRB with a 1 millisecond width. We also spec'd it to be able to provide community alerts, not just of the FRB, but of its initial localization within 60 seconds of detection. That was what we had promised to do, and that's what we were funded to do. And I'm pleased to report that that's our first dish. It looks rather nicer than the previous dishes that we had. A few features. We designed a movable mount in elevation only, so we can actually tell it to go to an elevation. It's rather a luxury for us. And we have transparent feed legs, a slightly more compact feed, but most importantly, a custom-designed LNA with a lab noise temperature of 6 Kelvin, which gives us a system temperature of somewhat under 25 Kelvin and a measured aperture efficiency of above 65%, which beats the spec that we had per dish by a factor of 1.5. And so we're pretty happy with this, and we're now ready to roll out into full construction. I'm just showing here scans across Cygnus A as function of time taken by graduate student Itika Yadlapalli, who pictured working away there. Right. We have an STM. We're a serious project. Uh, I'm not going to say much about that at all. Now, I just wanted to highlight some of the ongoing student and postdoc work within the group, starting off with Chris Bochenik, who also has spent a lot of time developing a system called STARE, which is sensitive to the nearest, brightest FRBs, which I actually think is really interesting, as I'll say a little bit more about in a minute. But we'll also be working on optical observations of the first 10 localizations. We also have Wendy Chen, whose work is highlighted here, and I'll say a bit about that in a minute. But she will also then proceed to work on the first 100 localizations. Nitika Yadlapalli has been putting in a lot of hard work in characterizing the antenna, but will move on to looking at various things like multi-wavelength counterparts, and also following up any repeaters that we see. And finally, Dana Samad, a time domain fellow in astronomy, has been putting in a huge amount of work to develop the calibration and interferometric correlation of the antennas, and we'll hope to use that for various kinds of ancillary science, but we'll also look at the scattering of the FRBs that we detect, applying expertise that she has. And I just want to highlight this work by Wendy Chen, where in preparation for having these really rapid alerts that we expect to have, we thought a little bit about the multi-wavelength immediate afterglows of FRBs, and just had some fun putting together different surveys of rapid events. I mean, of course, gamma ray burst surveys are sensitive to rapid events, as are some optical surveys. I mean, Gaia is, although it integrates for seconds. And what we did is we made a very simple assumption that none of them have ever seen an FRB counterpart. And then, taking that assumption, which of course may not be true at all, compared limits that we got on the fluence in each band divided by the fluence in the radio band, assuming a recent model, I think the James et al. Model for the FRB fluence distribution. What we get kind of interesting, which is that we find rather low limits compared to the published limits based on observations of known repeaters. And what's particularly nice is that at least the sort of external shock model of FRB emission seems to predict somewhat higher band-specific fluences than we actually would observe, assuming that we haven't seen an FRB in these bands yet, which is rather nice because it means that in order to test this, we may as well go out and try and look for these sort of sub-threshold or really faint events in the X-rays, which are, as it turns out, actually predictably detectable in these bands. It's kind of nice. So it basically motivates us to actually go out and do this sort of science. I have to apologize that I'm only sticking around today because we're presenting the DSA 2000 concept to the US Astro 2020 Decadal Survey Radio panel tomorrow. It's a concept that Greg Hallinan and I have been pushing for a next generation survey telescope. This will, among other things, do FRBs. That's pretty much all I need to say about this. 2,000 5-meter dishes with a sensitivity almost that of the SKA-1 mid, but with a 10 times higher survey speed. And so finally, a few wise words, hopefully wise words. Starting off, I think that it's fairly, it's becoming evident at least, that various observed properties of FRBs, such as the volumetric rate, such as the very fact that we can observe them, their fluences and their durations, the fluences, of course, relating to energetics, seem to indicate at least persistent, likely neutron star, that's at least my view, progenitors, often in relatively clean environments. I would say that this hypothesis is consistent with the localizations reported to date. I put this third point in small because it's kind of like, it's not really saying all that much. I mean, of course, if both young and old stellar populations are implicated, then possibly we have different progenitor channels. And the steps forward that I think are, at least the ways I would go in this field, are one, I really do think that getting at the nearest and most, but sort of pushing down the luminosity function, really getting at the nearest FRBs gives us a significant opportunity to study progenitor environments. So, for example, as the CHIME collaboration pointed out, this 22 megaparsec galaxy sitting smack in the middle of one of the CHIME localization regions, if that FRB comes from there, I mean, we could get less than 0.1 parsec resolution of this thing. It's pretty amazing with VLBI. Of course, I think the localizations are great. And I do think, and I apologize for putting this in the oddballs column. I'm not yet convinced that it is an oddball or not, but I think that the oddballs are really interesting, at least for the field. I mean, they give us something to talk about, right? And given that we've spent a long time talking about, a few oddballs, I think they really allow us to gain sort of really excellent insight. Even if they may not be representative, they give us a really, opportunity to have various ideas coming into the field. Thanks.